Swayam Prabha. Digital India. Educated India.
Today we will study geared system and branch system. This is a special kind of rotor system in which we don't have the single shaft, but multiple shafts are there and they are connected by gears, either to reduce the speed or to increase the speed of the shaft. And in this particular case, because the shafts are rotating at different speed, we need to take a special care for such system, and today we will see in detail how we can able to analyze the geared system and the extension of that as a branch system in which from one particular point multiple shaftings are connected through gears. So, let us see what are the things we will be covering. So, for geared system, basically we will try to convert the geared system to equivalent single shaft system. So, that whatever the previous analysis we did, we can able to apply for this particular system. For branch system, because multiple shafts are connected at one particular junction. So, for this particular case, we will use transfer matrix method, and subsequently we will be using finite element method in the subsequent lectures. So, various concepts which we will be introducing here is some are equivalent polar mass moment of inertia, equivalent torsional stiffness, junction point for branch system, gear ratio, etc. So, let us start with a geared system. So, in geared system, we have one shaft which is connected by heavy flywheel, and here there is a gear which is connected to another gear, and that is giving power to another shaft, and here another flywheel is there. Let us say this polar moment of inertia is IP2. So, the basically input is from here and we are getting output from this particular shaft system. Let us say this stiffness of this particular shaft, which is between gear and this flywheel, is KT2. Now, let us say we are mentioning this as shaft 1 and this is shaft 2, and in this particular shaft, let us say is having nominal speed of omega 1. Apart from this, because of the polar moment of inertia, it is having some torsional oscillation. So, let us say that is phi z 1, and because it is transmitting power, so is having torque T 1. These are at just before this particular gear, and basically this we will call it as pinion, and this is his gear, and this is gear. Now, if we to analyze this for torsional vibration, if we can convert this particular shaft system to a single shaft system, let us say we have this particular moment of inertia of the first flywheel and another flywheel is here, and they are connected by a uniform shaft, single shaft. So, we will try to convert the previous actual system to this equivalent system in which single shaft is there, and if we can able to convert, we already analyzed such system in which when this shaft system is mounted on frictionless bearing, we can able to obtain the natural frequency for torsion for this particular case. So, basically you can able to visualize this as if we enclose this particular gear system, including this second shaft and the second flywheel into a black box kind of thing, and the same thing is here. So, basically this particular polar moment of inertia will not be same as the previous one, because now we are talking about a equivalent system. So, let us say this is P equivalent, IP equivalent, and this shaft which was having stiffness KT2, let us say we are mentioning that as KTE. Here we have up to this point the gear. So, before this, whatever the stiffness is there is the same as the previous one. We are not converting this particular shaft to equivalent system. So, basically we are trying to find out the equivalent of this particular shaft system and this polar moment of inertia with respect to the input speed of the gear system. In this particular case, we are not considering the polar moment of inertia of these gears, we are neglecting them. But if we want to consider, then additional polar moment of inertia will be coming here. So, that will be giving us the system as 3 degree of freedom system instead of the 2 degree. For simplicity, we at present ignored this, but that can be added subsequently. So, here our aim is to obtain this equivalent system in which we, if we can find out what will be the new polar moment of inertia of this flywheel and what will be the new torsional stiffness of this particular shaft in this particular equivalent system in which single shaft is there. So, basically the principle will be equating the strain energy of these two systems, the actual system and the equivalent system, as well as the kinetic energy of this actual system and the equivalent system. So, these two energies should be same, then we can call these two systems as equivalent system. So, let us begin with the strain energy. For calculation of the strain energy, so what we will be doing, we will first we will assume that this particular disc we are giving we are giving a 0 displacement. That means, we are fixing this particular moment of inertia. Also here also we are fixing this particular flywheel. Now, we are giving input to the shaft 1 here and same input to this shaft here. So, here also we will be giving phi Z1. So, you can able to see that because of the effect of the gear ratio. So, let us see the gear ratio is what. So, gear ratio is nothing but the input velocity divided by the output shaft velocity. So, in our case, if we are talking about angular displacement, so these will be phi Z1 divided by phi Z2, or even it will be equal to omega 1 nominal speed of the gear. So, let us take the angular displacements as the gear ratio, in which the input angular displacement divided by the output angular displacement. So, you can able to see that when we are giving phi z1 input to this particular gear will be having opposite motion and different angular displacement. Similarly, if we want the nominal speeds, they will be different, torque will also be different. So, these are all at the location of the gear. This is the pinion and this is the gear. So, you can able to see that if we want to equate the strain energy in these two systems for a particular input. So, we are giving a phi z1 input, let us say we are giving a twist of phi z1 to this particular pinion in both the system, and we are trying to find out the strain energy in both the system. So, for first actual system, we will be having strain energy that will be, because the second shaft is having stiffness KT2 and its angular displacement will be this square. So, this is the strain energy in the actual system, and using this gear ratio we can able to write this as KT2 phi z1 by n whole square. This is for the actual system. For equivalent system, similar strain energy we can obtain, that is because the torsional stiffness of the equivalent system is KTE, and here if we again see whatever the angular displacement we are giving at this point, the same displacement this particular shaft is getting. So, here we will be having strain energy corresponding to the same displacement. Now, this two energy, because if these two systems are same, this two energy if we equate, because these two energy should be same. So, you can able to see if we equate these two, we will get KTE after cancellation of the angular displacements as KT2 divided by n square. So, this is the equivalent stiffness of the new shaft, which is given as KT2 divided by gear ratio square. So, you can able to see that this particular torsional stiffness we could able to obtain using this. Now, in the second case, we will release this flywheel. As we did earlier, we fixed it. Now, we are assuming they are not fixed, but now we are considering the shaft as rigid. For second case, these two shafts are rigid. That means, whatever the displacement we are giving here, this particular flywheel will be having same displacements, because now we are considering the shaft as rigid. Now, we will be obtaining the kinetic energy of these two systems. So, let us say for actual system, we have kinetic energy IP2 and the angular velocity is, let us say, this, and for the equivalent system the kinetic energy is IP equivalent, and let us say angular velocity of this is this. Now, this angular velocity which we have is having two components. One is corresponding to the nominal speed omega 2 of the second shaft plus the angular displacement due to the torsion angular velocity due to torsion. Similarly, the equivalent angular velocity or angular velocity of the equivalent system will be omega 1, because there is no gear in this. So, whatever the input velocity will be transmitted to the this particular shaft, and then torsional displacement or torsional velocity, that will be also be same. So, now this particular angular velocity we can able to substitute this in these equations, and if we substitute, so we will be having basically these two kinetic energy are same also. So, we can equate them also. So, half I p 2 omega 2 plus phi z dot whole square is equal to half I p e omega 1 plus phi z 1 dot whole square. Now, these displacements we can able to write like for phi z 1, we can able to write it as in terms of torque, and this is for first system in which the torque, this is the torque and divided by the torsional stiffness. So, we will get the angular displacement, and for second system, the actual system, T 2 divided by K T 2, and using the gear ratio we can able to write this as in terms of T 1 K T 2. So, these displacement we can able to substitute in these expressions. So, once we substitute these expression in kinetic energies of both the system, which we equated earlier, we will get omega 1 by n time derivative of the angular displacement, which we are replacing by the torque divided by the this is for the actual system, and sorry, this is actual system. So, this is K P 2 and this is I P E, this is for the equivalent system. Whole square. So, basically what we have done here, we have substituted these this quantity here and this quantity here, and we use the gear ratio to convert everything in terms of omega 1 or phi z 1. So, now you can able to see, once we take 1 by n common, we will get I p 2. If we take 1 by n common, this will be, because within the square, so we will get 1 by n square omega 1 plus d by dt. Here we will be having T 1 by K 2 n square and is equal to I p e omega 1 plus d by dt T 1 n square by K T e. Here we have converted this also into the K T 2. K T e is nothing but 2 divided by n square, so it is coming here. So now you can able to see this quantity is getting cancelled, and we are getting equivalent polar moment of inertia as this one. So we need to just divide the gear ratio square to the actual polar moment of inertia to get the equivalent polar moment of inertia. So once we have done this, you can able to see that now we know this and this, and this particular shaft, if it is having stiffness KT1, this is having KT1. So these two shaft segment, basically they are connected in series. So we can able to find out what is the total stiffness of this, and then we can able to as we did earlier for single shaft system, we can able to analyze for the torsional vibration. So I am not repeating that particular things here. Only thing will be the mode shape. So this is the equivalent system for two rotor system which we obtained. So if we are getting mode shape, let us say one of the mode shape will be having one node here. So and let us say this is the gear position. Gear position is here and node is here. So this is for the equivalent system. So if we want to obtain the mode shape for the actual system, so what were the displacements are there, angular displacement, because this is nothing but angular displacements of Z1, phi Z2. So angular displacements should be divided by the gear ratio. So we can see that after the gear, if this is the gear location, so all the displacement will be divided by n. So we can expect there will be change in the slope of the line, and this particular thing is nothing but phi Z2 by n. So mode shape will be this solid line up to the gear, and this dotted line will be the modified mode shape for the actual system. All the analysis will remain same as the previous one. Now we will analyze a branch system which is an extension of the gear system. In this particular case, we will find that at one particular junction there will be more than 2 gears are attached, so that the power which is getting transmitted from one particular shaft, it is transmitted to 2 or 3 or many shafts. Generally such application will find when we are having one main motor and it is driving several other shafts, and these motions are given by the various gears. So let us see how this particular system can be analyzed. So let us see first what is the branch system. So we have one shaft system in which we can have multiple discs. So let us say we have 1, 0, 1, several discs are there. Let us say p number of discs are there in a particular system. So this is a single shaft system. Now we are having another branch here. So this is a gear basically which is connecting another shaft system. So let us say this particular branch we are giving as the name as branch A. This is branch C, and at the top there is another branch which is, let us say, branch B. So basically this is a pinion and is driving this gear as well as this gear. These are various flywheels or discs in a rotor system, and we can have, like for branch B, we can have q number of discs. Similarly for branch C we have, let us say, r number of discs. So there are so many discs in this particular system, but main thing is this branching. So you can able to see that from one particular shaft the power is getting transmitted to 2 shafts. We can have more also, but for illustration we are showing only the 2. So, because this is a multi-rotor system, so we will be using the transfer matrix method, and for this we already obtained like state vector for, let us say, pth station of branch A, right side of the disk. So, basically this particular state vector is here, this is the branch A and pth station, and right side of the this particular gear is this particular state vector. We are relating this state vector with the state vector at 0 station, and let us say overall transfer matrix for this is A. So, this is the state vector at 0 station of branch A. So, basically this equation is representing the whole branch A. Similar expression we can able to write for branch B. In this particular case we have q number of things. So, this is equal to, let us say, overall transfer matrix for this is B, and this is the 0 station at branch B. Similarly, we can able to write for branch C. So, right of rth disk of branch C is equal to, let us say, this C is the overall transfer matrix for branch C, and this is the state vector at 0 station. So, here is the state vector, this particular state vector, and this is the right of rth. So, I should write it correctly like this. So, this state vector is right of this particular rth disk. So, these equations basically representing the governing equation for the 3 branches, but they have not been connected as is connected by gear. So, now we will be taking one at a time these equations and we will try to relate them. Basically, we will try to satisfy the boundary conditions which is there here or here or here or at the junction point. And these rotors, basically we are assuming that, as we did earlier, they are mounted on frictionless support. So, they can have torsional motion like this. So, let us start with the branch A. For branch A, we can able to expand this as like this. Let us say overall transfer matrix I am representing as A11, A12, A21, A22, phi z, and torque at 0 station of branch A. Now, the boundary condition at 0 station is that this particular torque is 0, because that particular end of the shaft is free. So, there will be torque 0 here, displacement will not be 0, and for simplicity, or because we are analyzing the free vibration, we are taking this particular station angular displacement as unity, and we will be obtaining relative to this what are the displacements of the other. So, we will equate this equal to 1, and this is according to boundary condition is 0. So, you can able to see that if we expand this, we will get phi z and A as A11, and the second equation T and A as A21, Now we will take the branch B. Sorry, this is P, I think. These are P because P number of disks are there in the branch A, and in this we have Q number of disk. So B11, B12. This is the overall transfer matrix for branch B. Here torque is there, and here angular displacement, zero station of branch B. At junction point between gear A and gear B, let us say gear ratio is NAB. So that is nothing but phi Z, that is pth station of branch A divided by phi Z. This is 0th station of branch B. So this is input, this is the output. So you can able to see that we can able to replace this particular displacement is phi Z PA divided by gear ratio, that is A to B, and this we already obtained earlier as A11. So this can be written as A11 divided by NAB. If we see the other boundary condition of branch B, at this station we have torque 0. So that means here torque is 0. So this torque is 0, and if we expand, we can able to get phi Z QB. This is the state angular displacement of branch B at qth station, is equal to B11, first equation, A11 divided by NAB plus B12 into T naught B. So this is the first equation. Second equation will give us 0 is equal to B21 A11 by NAB plus B22 T naught B. So we have two equations now. So now we can able to see that we can able to this particular equation we can able to solve for T naught B, and then we can able to substitute this in the first equation. So we are solving for T naught B from previous equation. So you can able to see we will be having minus 2B1 A11 by NAB, and then this will go in denominator B22. This is we got from second equation. This can be substituted here. So we can able to get the phi ZQB as B11 A11 divided by NAB, then B12, and this T naught B will give us minus B21 A11 divided by NAB B22. So now you can able to see we could able to get the angular displacement at in branch B at qth station, that is the far end of this one. Now we can able to take up the third branch. For third branch we can able to write the expanded form, that is C branch. So here we have R C is equal to C11, C12, C21, C22, phi z and t, and this is the zeroth station of branch C. So, here boundary condition is, because this end is free, so this is 0, and using gear ratio between branch A and C, we can able to write this as we did earlier for this. So, here the gear ratio will change A11 divided by and A to C. Earlier it was A to B, now it is A to C. Now, you can able to see that we can able to express again these expressions. Phi z or C is equal to C11 A11 by NAC plus C12 T naught C. This is first equation. Second equation will be 0 C21 A11 by NAC plus C22 C naught C. So, these are the two equations. Again, we can able to see that we can able to solve for this, and we can able to eliminate T naught C from here. Now, let us see, apart from this, at present we could able to relate the branch A, branch B and branch C using the gear ratio, and we applied the boundary conditions. So, now one another condition which we have not exploited, that is the junction point. Whatever the work will be doing at the shaft A will be equal to the work done at shaft B and C. So, let us see this particular boundary condition or this particular condition how we can able to satisfy, and once we will satisfy this, we will get the frequency equation from the our formulation. So, this is the last condition we need to satisfy at the junction point. So, this is the work done at branch A should be equal to the work done at branch B and C, and we can able to solve this for this particular torque. So, I have divided by the angular displacement of this, and these angular displacement ratios are nothing but the gear ratio. So, we can able to write like this. So, now I am solving for T naught C, this expression. So, T naught C is multiplication of this quantity, and if we take this in the other side, this quantity will be negative. Earlier we obtained T naught B. So, I am substituting this T naught B we obtained earlier, T naught B we obtained earlier. So, I substituted that expression there, and T naught, this particular T and A also we obtained earlier. So, that I have substituted as A21. So, this is T naught C. This is the equation for branch C which we earlier wrote. This was the boundary condition, this using gear ratio we converted, and this was the T naught C. So, basically this expression we are writing here, and now you can able to see from second equation, if we expand, we will get this expression which is not containing any other state vector like phi z or torque. They are containing only the terms related with the overall transfer matrix of branch A, B and C and the gear ratio. So, basically these transfer matrices coefficients, they are function of omega. So, this is a frequency equation basically, and we need to solve this using some kind of numerical technique which we have already explained earlier. This is the frequency equation, and in this particular case we will be having many natural frequency, and how many, let us see. So, in the branch A we had P number of disc, branch B we had Q number of disc, branch C we had R number of disc. So, total degree of freedom we expect this much, but the angular displacement of branch B at this point is related with this by gear ratio. Similarly, for branch C is related with this. So, that means two angular displacements are related. So, the degree of freedom will be that much less, because we have two additional constraints. So, these many natural frequency we expect from the previous frequency equation, and once we get the frequency equation, we can use transfer matrices to get the relative displacements at various locations to get the mode shapes corresponding to each of the natural frequencies. Let us take one example of branch system in which we can whatever the method we explained will be more clear. So, here we are taking a branch system. The branch system is similar to the previous one, only thing for analysis we have taken only the one disk in branch A, similarly another disk in branch this particular branch, and so we have not used multiple disks, only single disk we have considered in each of them. And in this particular case, these are the polar moment of inertia of various disks. Polar moment of inertia of the gears we are neglecting, and the gear ratio between branch B and C is 3, or between gear B and C is 3, that means between B and C is 3, and similarly between B and D gear is 4. Various lengths are given of the previous of the figure, diameter of the shafts are given, and even the material property of the shaft is given. So, now we can able to obtain the various property of this particular problem. So, these are the polar moment of inertia of 3 flywheel which is given to us. The second moment of area, polar moment of area, can be calculated. Even the torsional stiffness of each of the shaft segment we can able to obtain. This two shaft segment is having same property, so their stiffness is same. Now, we can able to write the state vector for branch A. In this particular case, we can able to see that overall transfer matrix is having only two components. One is the point matrix and field matrix, and we know the property of this. So, we can able to get the A matrix. So, in this we can able to see that this contain unknown as natural frequency. So, this is for branch A. Similarly, for this particular shaft, the third here, this particular shaft segment. So, this is the state vector at right of the that particular shaft segment. This is the overall transfer matrix for that branch. In this also we have only point and the field matrix, because we are not considering the inertia of the gear, and they can be obtained. So, this is the for that particular branch, this is the overall transfer matrix, second branch. For third branch, the lower one, that means if we see the figure, this particular branch, again we are writing the overall transfer matrix. So, this is also having one point matrix and one field matrix. So, they can be multiplied and we can get the. So, now we obtain all the branch overall transfer matrix. So, now the frequency equation which we derived earlier was of this form for 3 branches, and these are the various components of the matrix. So, this form A matrix, first row first column, this is C matrix, second row second column, like this. So, we can able to substitute this various terms from the 3 matrices which we obtained like this. So, we will get a expression like this, and if we simplify, we will get a polynomial of this form, and you can able to see that one of the natural frequency is 0 and other two natural frequency will be getting from this quadratic part. So, one natural frequency is 0, another are two natural frequency corresponding to the flexible mode, which we are getting from this. So, basically we have three natural frequencies. One of them is 0 natural frequency, which is corresponding to the rigid body mode, and these are the flexible modes. We will take up another example of a simple gear system in which two gears are there, and in this particular case we will obtain the frequency equation, natural frequency of the system, torsional natural frequency of the system. So, in this particular case also you can able to see this is the geared system in which this is the one of the flywheel, and this is connected by this particular gear to this gear, and this is another flywheel, and various property of these are gear, and in this particular case these are the flywheel property. In this particular case we are considering the inertia of the gear also, and other properties of the shaft A and B are given here, even the material property of the shafts are given. Now, with this property we can able to, now I am writing the transfer matrix, that is you can able to see this is for shaft A, this is the zeroth station of shaft A, and this is the right of one station. So, if you see this is the 0 station of shaft A, this is the 1. So, we have related the state vector which is here as right of A1, and this is the 0th station of branch A. So, we have related this by A matrix, where A matrix is multiplication of 3 point matrix, field matrix, point matrix. In this particular case, you can able to see that if we multiply these, we will get these expression for branch A. And for other shaft, similarly we can able to get the overall transfer matrix. Multiplication of this will give us this expression. At gear location we have this angular displacement relation using the gear ratio, and even the torque are related like this for, and these two can be combined like this. So, basically this particular matrix is nothing but for the gear ratio. So, we can able to see that using n matrix we can able to transfer the state vector from one shaft to another shaft. In between gear is there, having gear ratio is n. So, we can able to use this n matrix to connect the previous two equations or like this. So, now you can able to see we have related the state vector of branch A to branch B directly with the gear ratio. This is the overall transfer matrix, and this transfer matrix multiplication is given here. So, if we multiply them, we will get this transfer matrix, and for the condition free condition, we have already seen that if we apply the boundary condition from second equation, we get this as frequency equation. So, this particular term will be the frequency equation. So, after multiplication of this, we can get this expression. So, this is that particular frequency equation. So, if we expand this, and substitute the values of various parameter, we will get a polynomial of this form. And you can be able to see that from here we are getting frequencies which are, one is 0 natural frequency, other two are corresponding to the flexible mode. Just continue. In this particular case, because we considered the geared polar moment of inertia also, so when we converted or when we use the transfer matrix, basically we got a 3 degree of freedom system of this form, because this is corresponding to the gear system. So, that is why we are getting 3 natural frequency. One of them is 0 because free boundary condition. Okay. I will conclude now. So, today we seen the analysis of the geared system and branch system for its torsional vibration case. We obtained the frequency equation for both of cases. For branch, for geared system, we did some kind of equivalent. We converted the geared system to single shaft system, so that we can able to analyze with the method described previously for single shaft system, which is much easier to analyze. But with transfer matrix method, we have seen that for branch system, in which we have multiple degree of freedom, the TMM method is more advantageous, and we can able to get the rigid body mode and flexible mode depending upon the boundary conditions of the problem. And in the subsequent class, we will be extending the geared system and branch system analysis with finite element method also.